Hello friends, this video on Electrochemistry Part 8 is brought to you by examfear.com. No more fear from exam. So now the question is, how do we measure the electrode potential of other? Using standard hydrogen potential electrode. So let's do that. So if you see at STP at 298 Kelvin, I'm talking about at 298 Kelvin, my room temperature, so the EMF of the cell for this cell will be what? This is my anode, this is cathode. So this will be hydrogen electrode, standard hydrogen electrode and double bar, and this I have my second half of the cell, right? That is my cathode. So the first question is, why did I took as anode? Why did I took SHE by standard hydrogen electrode as anode? See, we need to find reduction potential, right? Because the electrode potential is nothing but reduction potential, correct? And IUPAC says reduction potential is nothing but electrode potential. Now if I keep this as my cathode is where I have reduction happen, right? So if you see E cell, whatever we will get from this is E reduction, that is this value, minus E oxidation, that is this guy, anode, and that is nothing but 0. So what will happen in that case? This value is something which you will get experimentally. This is unknown. So we don't have to apply any negative sign. So whatever value we got experimentally, that becomes my E reduction. So if you just flip it, then what will happen? This becomes 0 minus E oxidation. You assume this guy is oxidizing. And in that case, you have to apply a negative sign again unnecessarily. So just to make things simpler, you can actually do it other way around also. But just to make things simpler, I'll take standard hydrogen electrode as anode, because anyway I'm trying to find the reduction potential. And reduction happens at cathode. So that be a known. Correct? So let's find this for copper. So this is my copper. I'll dip in copper sulfate solution. So the reaction of the cell is like this. So here I have oxidation happening, right? That is my platinum coated hydrogen gas will get converted into H plus and double slash. This H plus is my electrolyte here, HCl or H plus, yeah, 1 mole. And then I have a copper sulfate solution. This Cu2 plus is my electrolyte here, and I get copper as the output. So this is my reaction, right? This is my whole cell representation, and this both H plus is 1m and copper plus is also 1m, because I'm talking about standard things now, all 1m. Correct? So for this, what we get is E cell is nothing but E reduction minus E oxidation. And this is 0. So experimentally we'll get this value. So E cell is nothing but E reduction, that is my Cu2 plus 2 copper minus E reduction, in this case E reduction potential of H plus 2H is 0, and E cell experimentally will found this to be 0.34 volt. So with this I can say that ECU2 plus 2Cu, this reduction potential of copper 2 plus 2 copper is nothing but 0.34 volt. Correct? That means for this reaction, copper 2 plus aqueous 1 mole to copper solution, obviously 2 electrons you need, the E value is 0.34. Correct? Now since, note one thing here is, since we assume this hydrogen to be 0, actually this is not 0, right? This is 4.4 volt actual value, but since this we assume to be 0, so we can't actually say that the standard electrode potential of this is this, we can say, but this positive value of this indicates that copper plus 2 ions get reduced more easily than H plus. It just indicates that copper plus 2 ions can get more easily oxidized, get more easily reduced than H plus ions because it has a positive reduction potential. Positive reduction potential, that means copper 2 plus easily gets reduced to copper as compared to H plus ions to hydrogen. I hope you understand. See, Cu2 plus to Cu, this has the value of 0.34 volt, and I am assuming H plus to H has the value of 0 volt. What does it mean? If you compare this, anyway, this was assumed. Since this was assumed, I got this value, right? Both are dependent. Compare these two equations. You can say that this positive value means this reaction is feasible, correct? More feasible. 0 means okay types. So when you compare these two, this 0.34 is more than 0. That means this reaction is more feasible, more spontaneous, I can say. The first reaction is more spontaneous than second reaction. That implies that copper 2 plus can easily reduce to copper. If you compare this with hydrogen plus, right? If you compare H plus and Cu2 plus, out of these two, it is Cu2 plus which will get reduced, not H plus. Why? Because Cu plus to Cu, it is 0.34 volt. It releases more energy. Gibbs free energy change is more negative. It's more feasible, right? Now I'm talking about reduction. Correct? Hope you understand. That means if you have in solution H plus and Cu2 plus, it is Cu2 plus that will become Cu. It is not H plus that will become H2. Right? That means if I have HCl and I have copper, HCl will not be able to dissolve copper. HCl will not be able to dissolve copper because H plus is not strong enough to convert Cu to Cu2 plus. In fact, Cu2 plus is easy. Say Cu2 plus to Cu is more easy than H plus to H2. Correct? Because for this to dissolve, H plus has to convert to H2. Then only reaction will happen. That will not be feasible. Correct? Let's find the same thing for zinc now. So instead of copper, we'll put zinc here. And we'll put zinc here. Now since we are putting zinc in the reduction side, so we have to write the reduction reaction of zinc. Correct? So here the equation of the cell will be what? My platinum surface, my hydrogen gas of 1 mole becomes H plus of 1 mole, double bond my zinc plus of 1 mole will become zinc. This is 1 mole like this. This is a reaction, and this is the whole representation of the cell. Right? For this cell, E of cell will be what? E of right minus E of left, that is E of Zn2 plus to zinc reduction minus E of hydrogen He. And experimentally this value is how much? Minus 0.76 volt. And that is nothing but E of Zn2 plus to zinc minus 0. So the reduction potential of zinc is minus 0.76 volt. Right? Now the negative value of this standard electrode indicates that H plus ions get reduced more easily. For example, now if we talk about these two reactions, this and H plus to H, this has the value of minus 0.76 and this has the value of 0. Out of these two, which one is more? Obviously the second is more because this is negative value, this is neutral value. Second reaction is more, that means the second reaction is more feasible than first reaction. And we have seen that zinc has a tendency to become Zn plus 2, not Zn plus 2 Zn, right? So if we compare hydrogen and zinc, So in that case, the negative potential of this indicates that H plus ions gets reduced more easily than Zn plus 2 ions. So now if you compare, we have H plus ions, we have Cu2 plus ion, we have Zn2 plus ion. So with these two values, we have seen that Cu2 plus ions get reduced more easily than H plus ions, and H plus ions get reduced more easily than zinc plus ions. Correct? And this is something which you can easily find using standard electrode potential. Correct? Now let's find, as I told, we found the EMF of the Daniell cell, right? Daniell cell is nothing but my anode is from zinc to Zn2 plus, and my cathode is Cu2 plus 2 copper. I am assuming both are 1 mole because the molarity of the electrolytes matter. For this E cell will be what? E naught cell, I'll say standard value. E naught right minus E naught left, right? Right minus left. What is right? Right is my E naught of Cu2 plus 2 Cu minus E left is nothing but reduction at right, Zn2 plus 2 Zn. Please note, it is not Zn to Zn2 plus, it is Zn2 plus 2 Zn. In both cases I am writing the reduction values. So Cu2 plus 2 Cu, we just found the value was 0.34 volt, and Zn2 plus 2 Zn, we just found the value was minus 0.76 volt. So if you solve this, you get 1.1, and that's how you get 1.1 volt. Correct? So if you see the standard electrode potential at 290, it is given for most of the reactions, and please note the standard electrode potential is nothing but standard reduction potential. Electrode potential is nothing but reduction potential as per IUP. If you see Fe state from 0 to minus 1, there is a reduction happening. Cobalt plus 3 to plus 2, reduction happening, right? You take anything. Au plus 3 to 0, reduction happening. You take anything. Br 0 to minus 1, reduction happening. You take copper, copper plus 2 to copper, reduction happening, 0.34 volt, the one we calculated, right? You will see lead Pb plus 2 to 0, reduction happening. All this reaction you will see reduction happening. All this thing, reduction. It's all, this is the reduced form, right? This is the reduced form, right? Al plus 3 to Al, reduction happening. Calcium 2 plus 2 calcium, reduction happening. All place you will see reduction happening, right? Now if you see the reduction potential of F2 to fluorine is 2.87. That means this reaction is more feasible, right? As compared to, now again here also for us, the hydrogen is the base, that is 0. Actually this value is 4.4. Right, the actual value, but it is assumed to be 0. Correct? This is all based compared to hydrogen. Now I'll show you how to read this chart actually, and it is a very important chart actually. You get a lot of info from this. See, if the standard electrode potential of an electrode is positive, for example these case, right? Yeah, I'll take gold. You know, gold is not reactive. That's something we know. Right? This is a stable form. This is a stable gold. So if the standard electrode potential is positive, that means its reduced form is more stable. So this is, if you see here, all positive, that means these are more stable. Why? If it is positive, that means the reaction is possible. Right? If the reaction is possible, that means the reduced form will be more stable as compared to hydrogen, as compared to hydrogen gas, because I am talking about hydrogen gas as a potential here. Now again, if the electrode potential of the electrode is negative, for example in this case, that means the hydrogen gas is more stable than its reduced form. So if the standard electrode potential is negative, for example in this case, that means it's reduced, that means the hydrogen gas is more stable than its reduced form. See, I am talking only about the reduced form. So that means in this case this is more stable and this is less stable. as compared to hydrogen gas, right? Because I'm talking about the reaction, I'm talking about the product. These are my product. So if this is positive, that means it is favorable to get this product, right? That means the product is more stable than hydrogen. If it is negative, that means it is not favorable to get the product, right? That means the hydrogen gas is more stable than this. So this is less stable, this is more stable than hydrogen gas. Hope you understand. This is one part, right? So if the electrode potential is positive, that means the reaction is more favorable. And since electrode potential is nothing but the reduction potential, that means the reduced form, that is the product, is more stable than hydrogen gas. If this is negative, that means the reduced form, that is my product, is less stable than hydrogen gas, right? And standard electrode potential is highest for fluorine. That means this is very, very stable, right? That means fluorine gas has a high tendency to lose electron and becomes F minus ion. This is F minus. And we have seen that all this chlorine, fluorine, bromine, they have tendency to lose electron because once they gain electron. Once they gain electron, they become more stable, right? F2 plus 2 electron gives F minus. This is very, very stable. Since they reduce themselves, they are very good oxidizing agent, right? They are good oxidizing agent because since they are getting reduced, they'll oxidize something else. So they are very, very strong oxidizing agent. Reverse is true for this. There will be very weak oxidizing agent or very weak reducing agent, yeah. Right? Same thing if you see, lithium has the lowest electrode potential, minus 3.0. That means this is not even favorable. This is more stable. Li plus is more stable. Correct? Now if we talk about this, this was a very strong oxidizing agent, as you've seen, because it has fluorine wants to become F minus. So that means if you go up, the oxidizing capacity increase. Fluorine is a very good oxidizing agent. Here also, if you go down, the reducing agent capacity increase because lithium plus is a very strong reducing agent because lithium plus wants to become lithium. Sorry, it is negative. This reaction is not favorable. So this Li plus to Li E is negative. So this reaction is not favorable. The favorable reaction will be Li to Li plus. Correct? Why? Why this is not favorable? Because this is negative. So this is favorable reaction. That means lithium wants to become lithium plus. Lithium is a very lithium oxidizes very easily. That means lithium is a good reducing agent. Correct? Lithium is a good reducing agent. This is a good lithium. This guy I'm talking about. Good reducing agent. Correct? Hope you understand what I'm trying to say. So reducing agent capability increase on the product side. On the reactant side, the moment you go up, the oxidizing agent capacity increase. And please note here, copper 2 plus to copper is a different value. Copper 1 plus to copper is a different value, right? So don't think that copper 2 plus or copper 3 plus or copper 2 plus to copper will have same value, right? They all have different value. See here, copper 2 plus gives copper E is 0.34 volt. Copper plus gives copper E is 0.5. That means this reaction is more favorable than this reaction. Copper 1 plus reaction is more favorable than copper 2 plus reaction, where both are getting reduced to copper because it has more EMF. Now we'll see what are the uses of the chemical cells. First is it is used to determine the pH of the solution. We'll see using Nernst equation you can actually find the pH of the solution using EMF. It is also used to find solubility product. We'll see some numericals on this. It is also used to find equilibrium constant. Here also we'll see some numericals on this. It is also used to find other thermodynamic property, and it is also used in potentiometric titration. So these are the various uses of electrochemical cells, apart from the fact that these chemical cells are used to produce electricity. That is the main use, right? Produce electricity, and that helps our laptops, mobiles, cameras, inverters. They run on these batteries, and they are nothing but electrochemical cells. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.